All right. So today we have Alice Lüscher, who will tell us about equivariant localization and holographic applications. Take it away.
Yeah, thank you, Julius, for the invitation. Hi, everyone. So today I'm going to tell you about some recent work I did in collaboration with Chris Cousins about equivariant localization and more particularly some holographic applications. So the context is SCFT, and what we will want to be doing is to compute some CFT observables such as the free energy, central charge. And from the supergravity point of view, such observables are obtained by taking some integrals over the internal space or subspaces of the internal space of our supergravity solution. So for example, the free energy would be proportional to the volume of this internal manifold. And at first sight, it looks like we need to know the explicit supergravity solution in order to perform this integral. We need a metric on M. And typically, it's difficult to obtain explicit supergravity solution and to solve the equation of motion. Like these are a set of highly nonlinear PDEs, and you will obtain solution like one-on-one, like for each supergravity. And we have some such solutions, but it's not an easy task. So the question we will want to be asking is whether we have a way to compute such observables, compute such integrals without actually needing an explicit supergravity solution. And the answer is yes, and that the tools we'll be using is equivariant localization. So this method has been introduced by Pietro Benetti Giannolini, James, and Jerome last year. And the rough idea is that to compute these observables, we would be integrating some n form over an n-dimensional manifold. And using this fixed point formula, equivariant localization, we can recast the problem as just evaluating some lower degree forms in some special subspaces of this n-dimensional spacetime. And so that's an easier task, and in particular, doesn't require the explicit knowledge of M. So in a second, I will make clearer what is the relation between these higher and lower degree forms and the precise form of this fixed point formula, what I mean by these special subspaces we're localizing on. But first, let me just make a few remarks about this structure. So really the power of equivariant localization is that we'll never be solving any of the supergravity equations. We will just pick some topology for the internal space and extract these observables only in terms of this topological data. And that allows us to obtain some results for theories that seem to be very different, like, for example, some CFTs with different scaling in N, which from field theory point of view, that would require some very different methods to be able to compute these observables. And here we obtain them in a very uniform way, just by building one set of equation using topological properties, we just obtain results in a straightforward way for all these different families of theories. So is there already questions? I don't think so, but just, yeah, in any case, feel free to interrupt at any points if you have any questions. So first, I will tell you what equivariant localization is, which is the technique we're going to be using. And then I'll turn to a specific supergravity setup we've been considering, which is massive type 2A on ADS4. And then I'll use the forms that we have in the supergravity to turn to two specific examples in field theory, some 3D Chern-Simons theory and some 5D theories work on a Riemann surface. And I'll conclude with some discussion. So what's equivariant localization? So what we want to be considering is some supergravity solution which has a symmetry. Here we'll take it to be a U1 symmetry, and in particular later we'll take it to be dual to the U1R symmetry of the field theory. But generically, to be using equivariant localization, all you need is asymmetry or U1 symmetry in particular. And to associate to this symmetry, we have a killing vector that will be denoting back psi. and from which we can build an object that is called equivariant exterior derivative, which is just the usual exterior derivative, and we're adding some contraction with the vector field. So this object naturally acts on polyform, which is forms composed of form of different degrees. I guess the exterior derivative would be raising the degree of a form by 1, while taking a contraction with a vector field is lowering the degree of a form by 1. So the polyforms we are interested in are what are called equivalently closed, which is if you act with this exterior derivative on a polyform that is closed, you get 0. And so explicitly what it means is that D on the higher degree form is 0, so the higher degree form is closed, which is kind of natural for the physical observables we'll be considering. Like typically we're interested in computing observables that are closed forms. And then at each order, like we'll be taking some contraction with the vector field, and that should be equal to D of the form of the lower degree, and so on, such that each order cancel each other. Like in this equality, we have n-1 form on each side, and so that they're equal, they cancel, and so on. And so we'll be building polyforms iteratively, such that each order in the polyform cancels when acted on by the xi. So why are we interested in these equivalently closed forms? Is because we have this fixed point theorem that was in the math literature since the 80s that is telling us that the integral of such an equivalently closed form localizes to only fixed point contributions. So we're integrating this polyform that is closed, the highest degree is by n on an n-dimensional manifold. And if it's equivalently closed, the only contributions that we get out of this n-dimensional integrals are contributions from subspaces that are like lower dimensional in this space-time. And the subspaces are such that the symmetry acts trivially on them, so they're invariant under this U1 symmetry. And then the contributions you have on each of these subspaces are just given by the lower degree forms inside of your polyform. So F is just picking basically the form that is of the right degree inside of the polyform to be integrated over such a lower dimensional subspace. And the only spooky object in this formula maybe is this equivariant Euler class at the denominator of the normal bundle. So you have this subspace, you have a normal bundle, and then you will be computed what is called this equivariant Euler form. And I'll be coming back to that in a few slides to re-express it in a form that is more usable for us directly on examples and make it more explicit what it is. But first, I wanted to make a comparison with supersymmetric localization, because I think most of the people in the audience, if you hear localization, you associate it with supersymmetric localization, and they're not unrelated concepts. So I just want to point out what's different or not. So supersymmetric localization, in some sense, is a particular case of equivariant localization, where the symmetry that you're picking, instead of being this U1 symmetry, is supersymmetry. And so then you also have some nilpotent operator, building some cohomology, and the kind of what plays the role of our equivalently closed forms are these BPS observators that are BPS observables that are killed by the supersymmetry. And typically, we would be computing some path integrals that would localize on BPS configurations. So these BPS configurations are exactly the ones that are invariant under supersymmetry. The same way here we're considering like invariant subspaces. And then you would have some classical contribution, and that would be dressed by some one-loop determinants. What we're doing here is that we'll never be computing path integrals. Here, we're really interested in computing integrals over space-time, but they also like localize on these fixed subspaces. And you can see like this kind of classical part. And then this Euler class is playing a role that is kind of similar to this one loop determinant. You can say it as dressing the integral in a similar way. Okay, if there is no question, I'll just go on about this Euler class. So we're going to try to understand better what this object is and to rewrite it in a way that is usable on our geometries. So Here we could be considering, like, for example, like a sphere rotated like by this U1 action, and you have a fixed point of the symmetry at the pole, and the normal bundle at the fixed point can be written like, for example, if it's if you have some embedding of the sphere, we could imagine that's some R4, and we will want to decompose it into some line bundles. So this is this decomposition into line bundles, and each of the line bundle is rotated under the action of the U1 symmetry with a specific weight. So here this del phi are rotating each of the line bundle with a specific weight. So that's how we want to decompose our normal space and our U1 action. So the U1 action acts on the normal space with specific weight on each line bundle. Once we've done this decomposition, our Euler class actually factorizes in terms of the first Chern class of each of these line bundles and the weight of the killing vector on each of these. Then it's just a matter of some binomial expansion. I put this bracket at the denominator and I can expand it. And why do I want to expand it? It's because this series typically is going to truncate. And so I just have a finite number of terms. And also, I only have one of the term in the series that is going to contribute for each dimension of the fixed point. So if I have an isolated fixed point as here, I'm just going to pick up this contribution. And on the other hand, for fixed surfaces, I would pick up like one Chern class. Fixed four-dimensional subspaces would be a higher order, but in this talk in particular, we're going to only be considering fixed surfaces at the highest. And so we would never get higher order contribution. So this object is basically just giving us some weights or some Chern class contribution. So in summary, that's the formula we will be wanting to use now that I've re-expressed the Euler class. So these integrals over n-dimensional space pick up contribution of subspaces that are of this form. And that will depend on the topology of M to actually be able to express this explicitly. So that's still technical, and it seems like maybe a difficult formula to use. So what I want to do now is just to give you a very easy example to show you how to apply it, and that it's not that difficult what's going into here. So we will just be computing the volume of the two sphere to just get a sense of what's going in there. So the metric I'm just taking the usual spherical metric on the two sphere, and so then I have a volume form, and I want to be computing the integral of this volume form. So I identify it as the top form part of some polyform, and I want to complete it into something that is equivalently closed, such that I can use my fixed point formula. So the killing vector on my sphere is just the one that is rotating the sphere, and it has the fixed point of its the fixed points are like at the two poles, and at these two poles I can see what the weights are. So I'm rotating this normal bundle with weight epsilon. You can see it as like some kind of velocity of the rotation. I'm just going the other direction at the other pole, so I'm just going to have a change of signs between the weights at the two poles. Then I can take the contraction into my volume form, and for the polyform to be equivalently closed, I want it to be equal to d of something. So if I'm contracting my killing vector into my volume form, del phi into d phi gives me 1. I get a minus sign from exchanging the wedge, and I can directly recognize this sin theta d theta as d of cos theta. So that's directly d of what's in the parentheses. And so I identify this object as the zero form part of my equivalently closed form. So now if I sum my volume form and this object, the total polyform is equivalently closed. I can go on with my machinery of this fixed point formula. And so the integral just localizes to the contributions at the two poles, just given by evaluating my zero form parts, which is here epsilon cos theta. So I just need to know cos of 0. So I have 1 minus 1 equal to 2 times 2 pi. I've obtained that the volume of the two sphere is 4 pi. Okay, that seems very overkill. You know how to compute the volume of a two sphere without equivariant localization, but it's easier. Like we didn't need to do like any integral. We just like knew like what cos of 0 and cos of pi was. So that's a bit how it works, and that's not going to get any more difficult than that on other topologies, basically. So that's the kind of computations we'll be doing, and when the integral is difficult to perform, that's very powerful to be able to use that. Any question on the example or? Good. Then just go on. So this idea that these authors had was to apply this fixed point formula directly in supergravity. So in that case, as I mentioned, like the U1 action, this psi vector field will want to consider is dual to the R symmetry of the field theory. So we're kind of guaranteed that we will have such a U1 symmetry in our supergravity solution. And then we will be able to localize either in the internal space of the solution, and that's the case I will be interested in this talk. But you could also imagine reducing over the internal space and obtaining some four-dimensional supergravity or something, and localizing on fluctuation of the ADS factor. I'll come back to that in the discussion, but this talk will really be using the internal space. So generically, we would need to use the Killing-Spinner equations and bilinears to build equivalently closed forms. So for the two-sphere, what we needed was to know that derivative of cos was equal to sine. But in general, for our supergravity, we need some relations between like some derivative of some fields and like some other fields. And so that's going to be encoded in some bilinears. And typically these relations between their derivatives are going to be coming from Killing-Spinner equations. And the point is that, so there are several remarks here. One point is that we'll never be solving these Killing-Spinner equations, but we can still like impose them. So there are some relations coming out of them, and we can impose these relations to build these equivalently closed forms. One thing is that we would not impose all of these equations, but only a subset of them. And so typically you get some off-shell results, and you would still need to extremize over some parameters to get the on-shell results. So, but that's going to become clearer in examples. We're going to get some off-shell things and go through the extremization. In this talk, though, like we won't need to use directly bilinears and Killing-Spinner equations, because some people have given us already some identities for the supergravity setup we'll be considering. So you won't see any bilinears. You can now forget kind of about it. I just wanted to mention that's where these forms are coming from. And really the power of localization is that you build these polyforms once. So you really need to like understand what your polyforms are. But once you've built them for one supergravity theory, then you can pick various topologies for your internal space, and so obtain various like field theory duals, and you will always be using the same equivalently closed form. And the process of localization is really like straightforward, like just picking some contributions from these fixed points. And so we'll be able to obtain very different results for all these classes of theories out of one set of polyforms. So if there are still no questions, I'll go on with the supergravity setup we'll be using. So here I want to specialize to massive type 2A on ADS4 and a 6-dimensional internal space. And the kind of observable we would want to compute in this setup are the free energy, which is just like the logarithm of the partition function. So that's an observable that tells us a lot about our SCFT. That's something very nice we're able to compute. We could also compute some fluxes that give like some integer characterizing like our field theory, such as the rank of the gauge group. We can also use localization to compute these. And another observable, we're able to consider some conformal dimension of some dual point-like BPS operator of the field theory that you would be obtaining by wrapping some D2 branes over some 2 cycles of the internal space. And so like the free energy would be proportional to the volume of your internal space. Here A is my warp factor and phi my dilaton. In terms of the fluxes in massive type 2A, we have 2, 4, and 6 forms fluxes that we could be integrating over subcycles. And here F0 is the zero form flux, which is the Riemann's mass over type 2a. Y is one of the coordinates, and here we would be computing volume of these two cycles. So now the game we want to play is to build some polyforms which are closed that allow us to compute explicitly these integrals. So for example, for the free energy, like we want the top form part to be our integrand, and then we iteratively build the lower degrees parts that are making the full form equivalently closed. And then we can play the same game for the fluxes and finally for the conformal dimensions. But I will only show you explicitly what's going on for the free energy here, but you can, I mean, we did, and not showing here what's going on for fluxes and conformal dimensions as well. So yeah, I'm sorry, I have to show you a metric, but it's not that difficult actually. So this is the most general form of what you can have for your internal space if you on ADS4, if you want to preserve n equals to 2 supersymmetry.
Question.
And yeah, sorry.
In the previous slide, how do you compute those forms?
So I'm gonna go to that in a second, but the idea is that you want to, if you contract psi into one part, you want to be equal to d of the lower degree and so on. So you construct them iteratively by considering contraction of your U1 action into the top form part, and you would like try to find the same way we're taking psi into the volume form for the sphere and being like, oh, what's the d of, is it? That's the game you're playing with these polyforms. And so you need some identities between like the different fields of your theory to like understand how their derivative or contractions are related.
And so it's like a descent equations? Maybe you don't know that, but the Lie derivative is defined for all of them. It's the same.
We're using the exterior derivative rather than the Lie derivative here, but I'm not sure I understand your question
The contraction
completely.
of the vector. You're saying that you're contracting with a vector, and so the contraction, this is a fixed vector that you are using.
Yeah, so for example, like in the case I'm going to show here, like your killing vector is like del psi, and so when you're contracting, you would just get some non-vanishing contributions from contracting into deep psi, unlike the rest would like the other contractions would vanish typically.
So once you fix the vector, you could compute all of those forms?
Yeah, they're really related to like which U1 symmetry you're picking. So,
and are there any ambiguities in solving the equations?
you could like add some constant at each order basically, but they would just like drop out from your integrals. So so these are really like homological statements. So like you can always like add some equivalently exact terms to your forms, and that would just like, and the integral are always like, I mean, the same, that's some cohomology. So like the theorem is like giving you like the statement for closed form up to your quotient by exact forms.
Okay, thank you.
Thanks for the question. Yes, so that is the metric on our internal space, so the most general one that preserve supersymmetry on ADS4. And so that just, if you want some S2 bundle over a 4-dimensional base, and this base is scalar, and we denote the Kähler form on this base by J. So the U1 action we're mentioning, you can see that there is no psi appearing, so we can like take it to be del psi. And again, F0 is our Riemann mass, either warp factor, and Y is just like this coordinate, but that's going to appear a bit in our forms. I want to stress out that it looks like we have a supergravity solution, but it's not exactly a supergravity solution because there are still some equations of motion that we would need to solve to determine what this G4 is. So that is not an explicit solution, and in particular, we won't be solving these equations to obtain results. So we will not know the explicit supergravity solutions of the examples we're looking at. So now maybe that answers a bit better the previous question. So from this metric, we can write down the volume form, which is basically just the wedge of the different thing and square G. And then when you take psi in, so D of the volume is 0, so the volume is closed. So the first condition is good. And then we want that at each order, if I take psi contracted in my volume form, that should be equal to D of phi 4. And by using some relations between the derivative of the Kähler form and the derivative of psi and so on, that these authors have been deriving for such a solution, we're able to find that actually that is the right form to consider. So D of that thing is indeed psi contracted into the volume. So I'm not like proving it here, but it's like a few lines of derivations using like identities from these papers to actually show that it is the case. So that's how you would be building the polyforms like explicitly. And once you have this degree, you contract psi into it again and say like this will give you 1 and this term would just like vanish, and you want to find the D of what is giving you what you've just obtained, and the answer is D of that line. And finally, you do the same to get the 0 form piece. So that's a bit how that works. And
yeah. Can you say more words on how F changes the sides?
Of what? What changes signs, sorry?
F goes to 1 over F in your expression from 4 to 2.
1 goes to... Oh, here? You mean like the F0, like the Riemann's mass? Why is it like at the bottom or not? Oh, actually, when you would be like compute, if you take psi into phi 4, this term actually drop, like psi into j is 0. So it's actually like this term that would survive. But then like dj is if you take like d of this thing, you would pick up some F0. It's just like the way like the forms are related. Not the forms, like the factors in your metric. So that is not coming from some relations that you can actually see on the slide.
Yeah. Okay. Very good.
So once you have this form, you will be interested in evaluating on some fixed point sets, and that's actually these expressions are like even easier on fixed point sets because typically dy is equal to 0 there. So these terms will just like drop. We needed to include them to like obtain like the lower order forms and make the form actually like closed. But once we'll be like evaluating on fixed points, this term won't be there anymore. So you can see that we actually get something that is very easy, just either like square in the Kähler form, proportional to the Kähler form, and with this y that we called was just like one of the direction in the metric. So these are objects that seem kind of easy to use. And in particular, if we go back to our fixed point formula, and we're like expanding in terms of the Chern class, we could like pick up some contribution from 0 like isolated fixed points or like fixed surfaces or like generically like fixed 4-dimensional space, but as they're not here in this talk, I won't write the contribution. And typically you only get contributions from one line or the other. And in terms of the polyform I've just like shown you to be closed, that's the kind of contributions we would have to evaluate. And it could seem at first sight that we've just like recast the problem. Okay, that is a bit easier, but like still we would need the explicit solutions to know what y is on the fixed point or what j is on the fixed surface. And actually it turns out to not be the case, and that these quantities evaluated at the fixed points really only depend on the topological data, and you can obtain what they are without needing the solution and just like in terms of these topologies. And so that's what and so now I'm gonna shortly turn to examples and actually be able to evaluate this expression and show you that it gives results. Any further question before I get started? Good. So What we can do now that we have our polyforms is to actually pick the topology for the internal space and go ahead and like evaluate on the fixed points. So here I'm going to be focusing on like two topologies of M6 that are respectively dual to 3D Chern-Simons series or 5D on a Riemann surface. And in these examples, I will be recovering results from the literature and not like actually showing you new results. So that may seem that all we are able to do is recover results, but that's not the case. It's just, okay, maybe I picked poorly my examples, but I still think they're a cool system and I want to show you how that works for these. But you could also consider other examples, and we did. And so in particular, you could wrap your 5D theory on a spindle, and there were already some results in the literature, but that were like conjectured, and we're able to prove them using our localization formula. You could also like consider just a random, not random, but like a topology for M6, like an hemisphere of a 4-dimensional base. And in that case, we don't even know what the field theory dual is. And we're still like giving a prediction for what the free energy of such a field theory should be. And the last thing that we would be doing, and that I'm going to show you in the example, is that this localization procedure gives us a geometric dual of F-maximization in field theory. So before jumping to these two specific examples, I'll just remind you like what F-maximization is, so you can enjoy like the geometric dual when it comes. So the idea is that you can take your 3D field theory, put it on S3, and gives it some trial or charges to compute the partition function. So you get a partition function that depends on these or charges. And then you will want to extremize the partition function with respect to these R charges under the constraint that the superpotential has an R charge 2, which gives you like some constraints over your R charges. And upon extremizing with these constraints, this will pick out actually the R charge assignation that is like the superconformal R charges. And so like the on-shell free energy would be like in terms of like the superconformal R charges. And we'll see that we can get something similar in gravity. So the first example I want to consider is to take my ADS4 times an internal space that is the suspension of a 5-dimensional Sasaki-Einstein. So the suspension, you can say as a sine cone. So just pick your favorite cone metric, replace R squared by a sine. So that's naturally like caps off on both sides in this kind of smoother way than a cone. And then I want to probe that geometry with a stack of D2 branes. And so I naturally got some 3D Quiver theory out of my word volume on my D2 branes. So if I take a stack of n branes, I get a gauge group of rank n. And I could like generically consider like any Sasaki-Einstein, but for the purpose of this talk, I will be focusing on the simplest case that is picking an S5. And then I also want to probe with a stack of D8. And so from the supergravity point of view, this D8 gives rise to the Romance mass of my massive type 2. And they're dual to some Chern-Simons level on my field theory side. So now I want to go ahead with localization. So what is our symmetry in that case? That is the symmetry that is rotating our S5. So we can see this S5 as embedded into an R6. The decomposition into line bundles is in terms of 3 copies of R2. And so my killing vector will have some weights that is rotating each copy of the R2 inside of the R6. And like the fixed point of these actions are at the 2 poles of the suspension. Then we can go ahead and, yeah.
This is a question about scaling. So in your previous relation, you related the Romance mass, which has a scale, to a level which has no scale. So
yeah, there is a Planck length in this relation. I think there must be like a string length maybe in the relation. I think that's like 2 pi the string length time the Romance mass that is equal to like the flux is the zero flux, and this zero flux is equal to the Chern-Simons level.
see.
So I think that's the string length that is taking care of the scale we're mentioning.
Okay, thank you.
Thanks. So now we can use equivariant localization to compute some quantities of this system. So I haven't shown you before the explicit equivalently closed form for the flux, but we built one. And here we don't need the explicit form. The only point is that when we want to integrate the sixth form flux over the internal space, we pick up some contribution from its zero form part at each pole, and we can evaluate these contributions. And in particular, that allows us to re-express this string length in terms of the n, which n is now our physical quantity, as it is like our number of branes at the level of our gauge group on the field theory. Then we can use like some other integral and some cohomological relation. Like the main, again, using equivariant localization, the main point is that we get some expression for the y that is appearing in our in our forms in terms of like this just topological data, this number of branes n and k. And so if we insert our expression that we found for y and that we find for the Planck length inside of a localization formula for the free energy, we eventually obtain a result that only depends on this k and n. And here we still have some dependence on the weight, and that is because actually the result we've just obtained is an off-shell result. So that's what I was mentioning of us not imposing all of the equation we can. So we get off-shell results, and we should still be extremizing over the weights. And we're extremizing the free energy over the weight is like this kind of geometry, like this dual of F-maximization in field theory, also because our U1 symmetry is like dual to this our symmetry killing vector. So we're kind of extremizing over our charges in some sense. And here we also have a constraint, but in gravity it's coming from requiring that the killing spinner has the right charge under this U1 symmetry. And if you go ahead and extremize this F with this constraint, you would find that all these weights have to be equal and equal to 1/3. And from this geometric point of view, the interpretation of this extremization is that the quantity we're actually extremizing in geometry is the volume of our internal space. So typically you can see the volume of the S5 in terms of this weight of the killing vector, and actually doing the extremization of this off-shell volume with this constraint, you would also find that the assignment of the weights that extremizes this volume is to take all the weights to be equal and equal to 1/3. And inserting this result inside this off-shell volume, you just get the on-shell volume of an S5. So this has so here I was focusing on the S5, but this volume interpretation is in terms of the weights is actually more general. And if you go ahead and do this computation for a general Sasaki-Einstein, you would find an expression for the free energy in terms of this off-shell volume of the Sasaki-Einstein. And so now if you specialize to S5, you recover what I was showing before, and in particular going off-shell, the free energy you find matches the one that had been obtained for field theory in that paper. But if you keep the Sasaki-Einstein more general, then the dual field theory you would get are some more general Quiver Chern-Simons theory. That's the one I was showing on the previous slide, in particular with more gauge groups or at level n, but maybe with different Chern-Simons level where the Chern-Simons level should sum to a number of T8. And depending on the Sasaki-Einstein, you can modulate the matter content of your dual theory. And then you would get that's for all this theory, the free energy is given by this expression in terms of this off-shell volume of the Sasaki-Einstein, and you would be extremizing over these parameters to get the on-shell free energy. One point that is interesting to mention is that when I was showing you this suspension and showing you this result, I assumed that I would get the same Sasaki-Einstein at both poles of my suspension, but I could also imagine taking a geometry where I have a different Sasaki-Einstein at each pole, and localization straightforwardly give us the results of the free energy of such a theory. And that's very interesting because the dual field theories of such geometries are not known. And so we're really making a prediction for what the free energy of this field theory should be if we're able to build them. And that's really coming easily from our localizations computations. Any question here? Otherwise, I'll go to the second example. Okay. So the next example I want to consider is taking some ADS6 on some sphere with some D4 branes and an O8 plane. So naturally, out of my D4 brane, I have some word volume theory that is a 5D SCFT. And now I can take with some, so that's the 5D quiver that I'm drawing. So you have a stack of ND4, and that is an SP gauge group of rank N. And then I can also add some D8 to my setup that would like give rise to my Riemann mass in massive 2A and be dual to my number of flavor on my CFT. And now I can take this 5D theory and wrap it on a Riemann surface. And what it corresponds to on the supergravity side is to go to the near horizon of this ADS6. And so I get an ADS4 factor and this same Riemann surface. And so now I identify in terms of my previous setup, that was ADS4 times M6. And with M6, the internal space, I can see this internal space as the Riemann surface and an hemisphere. So that's the internal space I want to localize on now. And now I'm writing an hemisphere rather than a sphere because of the O8 plane that I can see as capping off my sphere.
What happens if F0 is 0 or negative?
So I don't want to take it negative. I'm like not putting more than 8 branes, 88. I'm not sure anymore if you can actually put 8 or if you want to be strictly smaller than 8.
What goes wrong? Why you don't want it?
I think you can, depending on the setup, you can turn off or not F0, but I think that in this geometry, you don't want to turn off like F0. You have some degeneracy of like some of the forms that you don't want to allow. So you, as we had seen, like there is some F0 at the denominator sometimes and so on. So typically you don't want to turn off the mass. You really want to stay in massive 2A. So
And
here
what
we
about
will.
0?
But sorry?
The critical value 0. How about that?
Yeah, that's the one I don't think you can have. Like, I'm sure you cannot have it negative. Like, that's really a setup that is defined for less than 8 D8 in the system. And the critical value, I think you don't want it either because of this degeneracy. Like, you want to keep your theory massive. But I'm sorry, I cannot give you some more conceptual answer. Like, I know that these theories have been built this way, but physically, what's the obstruction? Like conceptually of turning off this mass, I'm not sure at the moment.
So you're dealing with ADS6.
Yeah, but I'm going to, when I'm wrapping on the Riemann surface, I'm actually like looking at near horizon geometry, some
I see.
inside of the ADS6. So that's why I end up with an ADS4 factor, and I can reduce back to like my setup from before of massive type 2 on ADS4 and 60 internal space. So that's why I'm not really
sigma.
Sorry.
Before you take sigma, it could become ADS7 instead.
Maybe, but that's not really like, I think I would like need another set of polyforms to deal with that. Also, that would be odd dimensional. I'll come back to that in the discussion, but that's just like a different system. I don't think I would be able to like study it directly with the polyforms I have in this setup I'm considering here.
Okay, thank you.
Okay, so yeah, we want to consider this 5D theories on the Riemann surface with now the topology for our internal space being this Riemann surface and a 4D hemisphere. So the way we want to see the 4D hemisphere is in terms of two line bundles, the sum of two line bundles fibered over the Riemann surface, and the degree of the vibration is by definition like the integral of the first Chern class of this line bundle over the Riemann surface, I denoted by P. And these P's have a natural dual in field theory, which is that when I put my field theory on the Riemann surface, I turn on some gauge field in order to preserve supersymmetry. And then like the integral of these gauge fields over the Riemann surface have some magnetic charge that are exactly these PIs. So that's the interpretation of this degree of the vibration in terms of the dual field theory. And so then my Killing vector in that case is rotating my hemisphere, and so the del phi are rotating the two line bundles with a certain weight epsilon. And so typically the fixed point of the action is at the pole, and what's fixed there is the full Riemann surface. So we get some two-dimensional fixed point. So we'll get like some different kind of contributions in our localization formula than the one we had in the previous examples. So one thing we can be computing there is to use localization to obtain some fluxes. So again, I hadn't shown you the explicit form before, and again, we don't really need the detail of the solution. The main point is that we can either pick up contributions from isolated fixed points or from fixed surfaces, depending on which kind of force cycles we want to integrate our four-form flux. So one of the force cycles of our geometry is the hemisphere itself, in which case the fixed point is just like the pole itself. And we pick up a contribution from this term of our localization formula. From this expression, we can find an expression of this y at the pole in terms of n. So again, we're getting rid of like the kind of coordinate and like solution dependent data in terms of just like topological data and like just really physical parameter of our system, this n. And then like by considering other force cycles, which we can take to be like a copy of the line bundle together with the Riemann surface. Instead, what would be fixed is the Riemann surface. And so we pick up contributions from another term. And from there, we can deduce what's the integral of the Kähler class of the Kähler form on the Riemann surface in terms of, again, these topological parameters, these n's. And we, on top of that, have some cohomological relations between these fluxes on these cycles and like the flux that is actually appearing in our field theory, that is like literally the gauge group of our field theory. So we can re-express everything, the y's, the j's, just in terms of this n, and in terms of the Chern classes that are the PIs, the degree of our vibration. And so when we want to now compute the free energy, our fixed point formula is telling us that it's given by just localizing on this fixed surface, and we can insert what we found for y, for j, that the Chern classes are these vibration parameters, and that's the result we would obtain, where n0 is proportional to the Riemann's mass again. And so what we want to notice here is that, again, we obtained an off-shell result that is in terms of these weights, and say, again, we want to extremize over these weights, but they're not independent. Again, they have to sum to 1 for the Killing spinner to have the right charge. That's this equivalent of like F-maximization under the constraint. So we can reparameterize these two weights in terms of a single variable. I denote by just a nicer epsilon, and that's the variable I will be extremizing over. And also we note that the vibration numbers are not independent parameters, but they have to sum to something in terms of the genus of our Riemann surface. From the geometry perspective, this constraint is coming from requiring that the internal space is a Calabi-Yau threefold. And from field theory, you can recognize just the topological twist constraint. So we can also parameterize these two parameters in terms of a single parameter that I call Z. And kappa is just a sign that is taking care of what the genus of the Riemann surface is, and we can obtain results uniformly for the different cases. In particular, I can take some limit to 0 to obtain the torus results. So if we go ahead and put these reparametrizations in F and then extremize over this nice epsilon, plug back the value, the extremal value of this epsilon, the value that is extremizing this F, we obtain an on-shell free energy for that system that reproduces what these authors had found. So the explicit expression of the free energy is not that important for us. I mean, we see some scaling in N, but we also see it's like not a nice expression. And in particular, it took a lot of work to these authors to get it in their paper. And like they had to solve the supergravity equation of oceans to obtain like this explicit supergravity solution with this Riemann surface and then like go ahead and stuff. But for us, that was 10 lines of Mathematica. Like we haven't solved anything. We have like isolated y's and j in some like linear equations. Like that's really just a lazy method to get like these observables. And so I think it's like really powerful. So let me just show a last, so I promised you some observables and I've only been computing free energies. So let me just show another observable that we can compute. So these conformal dimensions of these BPS operators. So we're wrapping the two branes on some two cycles. And then if the two cycles is entirely fixed, we'll just be computing its volume that is proportional to the Kähler form. Or if it has some fixed point on this two cycle, then localization is giving us that we should just pick up some zero form contribution on the fixed point. So the kind of two cycles we can consider is either this line bundle inside of the hemisphere. Yeah.
These are half BPS?
Yes, there are half BPS.
Half BPS, and we have there is sigma, so you have 8 supercharges at the conformal point, or 4?
I think so that's n equals to 150, and when you compactify in the Riemann surface, you get some n equals to 2 3D theories.
Mm-hmm. Okay, I see. Okay, thank you.
So one of the possibility for this two cycle that you can wrap and obtain some dual operators is just to wrap a copy of one of the line bundle, and in that case you have the pole that is a fixed point, and you would pick a contribution of this form. We've seen before that we know what y is in terms of m, and we can reparameterize our epsilon in terms of this nice epsilon. So that's one of the possibility. Or you could imagine wrapping the Riemann surface itself, in which case it's entirely fixed, and you get some other kind of contribution by plugging in what we found for the Kähler form in terms of m. And then we can use like the results we had for this epsilon that extremizes the free energy. So we've been through this extremization procedure. There is a specific epsilon that is extremizing our free energy, and that's the one we will want to put in here to get the on-shell conformal dimension. And again, we reproduce the results of these authors, but we could imagine applying the same techniques to get like some results that were not already in the literature. So if there is no question about that, I will conclude. So here I focused really on this massive type 2A with this 6-dimensional internal space. I've been showing you these two examples where we were recovering results, but we are also able from the same equivariantly closed forms to actually be considering some other topologies for M6 that are in the paper but not in the talk. And in particular, putting a spindle rather than a Riemann surface and getting some kind of block formula of shell that you can then extremize again to get like some on-shell results. And we're also like producing some results by picking some topologies for where the dual field theory is not known. We're like predicting what the free energy of such a putative field theory should be in case it exists for such a geometry, which is, for example, the case of this example. And as I've shown you, we give like some geometrical interpretation of what's going on for F-maximization in field theory. So I hope that I convinced you that equivariant localization is a powerful tool to extract holographic observables without ever solving a supergravity equation of motion. So that also allows us to access larger families of theories where like we don't actually know the solution, but we're still able to compute things. Also that the hard work was into like building what these polyforms were, but then we're able to just use them on all these different topologies. And in particular, the two examples I was considering, they have different scaling in n, so different tools required. And here we use the exact same tool and get like the answer in a few lines. So here also I've been focusing on localizing on the internal space, but you can very well just like reduce over your internal space and be considering like supergravity on the ADS factor and like fluctuations of ADS and localizing on there. And you get some very nice results as well. And you could also like consider some new horizon black hole geometry in these ADS factors. And that allows you to like compute properties of topologically twisted CFTs rather than just like the CFTs on flat space or on S3 as I was considering here. So I've been hiding a few things under the carpet that I'll just be discussing briefly now. So for example, when we're considering the hemisphere, there was like a boundary to our system. And so typically we should be considering boundary contributions to our integrals. And in the example I was showing, actually all the boundary contributions were vanishing. So I was allowed to put it under the carpet. But generically, if you want to consider these kind of geometries, you should be able to deal with boundary contributions. And you are interested in considering such geometries because it consists of like adding some flavors on your field theory. So that's something you want to be able to do and that we're working on at the moment. Another thing is that I told you that to do equivariant localization, what you need is a symmetry or a U1 symmetry. And I was taking it to be like the dual of the R symmetry. So we're looking at supersymmetric theories. But generically, we could imagine just using a solution that is not supersymmetric and that just has a U1 symmetry we can use for equivariant localization. And another thing I was putting under the carpet is that everything we're doing was requiring that our internal space was even dimensional. In particular, the polyforms we're building were even like each degree of the polyform was even dimensional. And that's where the localization formula take the form that I've shown you. And in the math literature, there are some generalization of these theorems for odd dimensional spaces, but they've never been applied to supergravity yet. And so that would be interesting to be able to apply this more general theorem also in supergravity to look at odd dimensional solutions. And one thing we're expecting to be able to do as well is to include higher derivative corrections in supergravity, which would correspond to being able to reproduce subleading corrections in N on the field theory. So here I was really showing some large N results, but there are a lot of subleading correction terms that I've been computing in field theory and that we think we should be able to reproduce with localization. I mean, it's exactly the same of building equivalently closed forms. And yeah, in particular, we should be able to add a lot of these and now what I wanted to say is that the structure of like the results only depending on the topology and not the explicit solution seems to show that there is really some underlying structure that is similar in all of these theories, and that should hint to something more fundamental about the structure of all these solutions. So I will stop here and thank you for your attention.
All right, let's thank Alice. Do we have questions? Or rather more questions? Okay, I would say since you already got quite a few during the talk, let's thank Alice again and we'll go off the record.